online people cannot
All right, good afternoon, everybody. Well, thank you for coming. This afternoon, we have Professor Abhishek Gupta giving us a seminar on the mathematics of AI. Professor Gupta is a professor in ECE at Ohio State, and he got his master and PhD from Illinois. That's right. So, anyway, so, Abhishek.
Thank you so much, Stephanie, for the
And
introduction.
I'll keep track of the questions online.
Yes.
So the chat.
Yes.
So hopefully, I'll do my best to get track of the chat questions.
Yeah.
Thank you, Abhishek, for coming.
Okay. Yeah, so basically the reason why I created this presentation, so I don't necessarily work in GenAI. But about a year back, there were a lot of people in a lot of different forums talking about how generative AI has consciousness and the world is coming to an end and whatnot. And I was like, somebody needs to stop this BS going around on social media. And then I realized, well, I'm an associate professor now, so maybe I'm supposed to stop this BS. So I made this presentation to basically dispel all the myths about generative AI. And the way to dispel the myth is basically to understand what the mathematical foundations are. And so even though generative AI is a very fascinating subject from a mathematical point of view, I understand that many of you are not an expert in advanced probability theory. So what I've done is stripped all the probability information from generative AI and just giving you a very crux of what exactly generative AI technology is about and how does it differentiate with other areas of machine learning that we are all very familiar with in today's world. So the way I'm going to proceed is as follows. I'll first talk about what generative AI is and where we are using generative AI in today's world. Then I'll introduce some basic mathematical ideas, some basic notation. And then I'm going to divide the presentation into three separate categories. One is where prompt dimension is less than content dimension. One is where prompt dimension is equal to content dimension, and where prompt dimension is much, much larger than the content dimension. And then I'll give a very brief overview of what future mathematical developments are ongoing in the generative AI world. And then I'll conclude the discussion. So generative AI basically is a function that maps input to output. So that's not very surprising. We all understand what input-output systems are, especially because this is Center for Automotive Research. So this is what you guys research on. The only difference is now, in this case, the input is a very high-dimensional random vector, or it could be a text prompt, which generally gets converted into a very high-dimensional vector via different machine learning models. So ultimately, the input, like we are all used to controls input, and controls input is typically 2-dimensional, 5-dimensional, 10-dimensional. Now we are talking about 100-dimensional or 500-dimensional or a million-dimensional vector. So that's what an input prompt means in this particular case. And the output in the context of generative AI typically is an image, a text, a video, audio, or a video with an audio. A lot of these things are so video with an audio is still a little bit far away, but you can generate a video and you can generate an audio using generative AI prompt. Not sure if any of you have heard of this company called Suno.ai. You can give it a text prompt and it will create a music out of the text prompt. And I actually like their music. Yeah. I got hooked onto their music and then I immediately stopped at some point of time. So if you think about it, people generally need suggestion nudges, images, video, search results, and so on. And basically, the way we tend to do it is we go online, we look for, we enter some keywords, and based on that, we get the information that we are looking for. So basically, whatever you are entering is basically a prompt, and whatever output you're getting is content that you probably need. And that's the way the value gets created in this particular ecosystem. So I go to YouTube, I want to learn optimization, I search Professor Gupta's course on optimization on YouTube, and then you get my course on YouTube, and then you go through the course, and that's what creates value in that particular context. So where exactly are people using generative AI? So I talked about the song generation part, the video generation part, but actually in other areas such as insurance underwriting, people are exploring. So all of this is not something that is in production, but it's something that people are still exploring. Insurance underwriting, legal case search and contract drafting, search and recommendation, social media content generation, script ideation for movies and other marketing ideas. Marketing and branding material and customer support. So these are all the different areas. So customer support is actually live, and some of the leading companies have completely automated a large part of their customer support and are saving a lot of money by using generative AI. But if you think about it, all of them are predominantly text-based generative AI systems, which means that even if there is an audio input, it gets converted to text, which then gets converted to a high-dimensional vector, which then goes through LLM, and then output comes out, and then it's converted into audio. So the core of it is generally a text-based Gen AI system at this point of time. But if you think about like towards the end of the end of this particular presentation, I'm trying to convince you that the theory actually is much more useful in other areas as well. The use cases that are currently not being looked at by many people. So one is user generation. So basically, whenever you are a developer, you want to know how a user is going to interact with the app that you have developed or with a website that you have developed. So user generation is a very critical problem because you can only get feedback once you put the app live. Before that, you can't really get a feedback. So if there was a way to generate phantom users who can then interact with your app, it would be a great help. You can also come up with dynamical systems model generation. So this is known as digital twin. So we have this building, we have a thermal management of this building done by 4 air conditioning systems that are in the back of the building, and a bunch of air handling units that are all over the ceiling in every room and in every floor of the building. So if you know what the input output behavior is, for if you are logging all the data, actually the university is logging all that data, and the data goes to Property Analytics, another company. So you have all the data log, you want to create a digital twin of the car's thermal management system, you can actually create it using the theory of generative AI. Of course, nobody is doing it. Not quite sure why somebody would be interested in doing it, but I know that GE specifically has been looking into the digital twin concept for a long time, primarily because of 2 reasons. First, they want to figure out how to optimize the system. And the second one is they want to detect if there are any ongoing cyber attacks on the system. They have large wind farms, they have large aerospace engines, and then they want to see if something wrong is happening within that system. So they want to create a digital twin of those systems. So again, the theory is quite useful for developing digital twin as well. Then automated app testing, we already talked about automated penetration testing. So penetration testing is typically done for assessing the vulnerabilities in a dynamical system, like maybe even in a software system. So you can use, if you know what the steps of penetration testing is, you can ask a Gen AI system to do the penetration testing for the software that you're using. So all of that can also be done using generative AI. Then marketing campaign generation, travel itinerary generation, and medical image cleaning. I think medical image cleaning, people already know that generative AI is useful there. So they've started using generative AI for cleaning of the images. So what I mean by image cleaning is, let's say you go into an MRI machine and you moved a little bit. So MRI is supposed to, let's say, capture your heart. And because you moved or the heart moved or your heart is pumping blood, so all of that creates noises in the image or in the feed that is going into the MRI machine. And so then the question is, how do you clean it up? How do you denoise those images? So that's where generative AI techniques are getting utilized. The reason why I know about this medical image cleaning is because I was in a student's candidacy exam just a week back, and I saw that some of the techniques that student was using is akin to using generative AI for medical images. So now that we know that what generative AI is, I want to give you a little bit about the theory, the history of generative AI. So underlying theory actually dates back to the 1930s. So at its very crude level, generative AI is all about optimal transport theory. Optimal transport theory had a lot of development in 1930s, 1920s to 30s. But now, of course, but optimal transport theory is very abstract. So, of course, there is a reason why all of this development happened in 2010s and 2020s. The reason being that we now have large publicly available data sets which are created by very talented individuals. So, specifically, if you look at Wikipedia or stock photo artists, they are all very competent people who are generating those texts and those images and so on. Which allows us to have very large publicly available data sets. Then we have large distributed computing systems due to the cloud, and then the knowledge of how to run gradient descent on them. So of course, gradient descent algorithm is something that we all know about. At least I teach it in my 5500 class. And so whenever I talk about gradient descent, of course, I'm assuming that everything is happening in one server. But if you imagine about the large language model training, it kind of happens over thousands of servers, thousands of GPUs. So how do you run gradient descent on thousands of GPUs? Now, of course, we know about it because people have been trying to figure that thing out for the last 7 or 8 years. So there is knowledge of how to do very large scale optimization. We have new abilities of training arbitrary large function approximating classes. So we know about neural networks and convolutional neural networks, and I'm sure many of you might have trained those in your research projects. Now, of course, in most of your research projects, you would be doing it in a single server, but sometimes these function approximating classes could be arbitrarily large in the sense that there are millions or even trillions of parameters that needs to be optimized, as is the case in the large language model. So now we understand how to train those kind of function approximating classes. And then we have years of knowledge about what does not work or is very hard to train. So I think a lot of people tend to focus a lot on things that are already done and is successful, but one should always keep at the back of the mind that every success is built upon thousands of failures. And so we know a lot about failures now. We know since 1990s to 2010, there has been a lot of failures in the area of machine learning and AI. And so we know a lot about what doesn't work. So, whatever you see today is based on those failures. And then we also have years of knowledge about what improves training performance. So just because we know how to do gradient descent and just because we know how to create servers, distributed server systems, it doesn't mean that we know how to run successful training. What are the hyperparameters that will lead to the best training performance, the best output, and so on. So of course, now we know a lot about that as well, because a lot of research has gone into it in the past decade. So all of that actually is important and critical factor for being able to create a generative AI system that we see today. So any questions so far before I jump into mathematical idea? Okay, so what I wanted to show you, this is a scatter plot of something, okay, some distribution. This is basically, I think I picked it up from Wikipedia. I don't know what this scatter plot is for, but we have all seen scatter plots of various types. And so you can see, you can imagine that every content that you see, every image that you see, every audio that you think about, all of that, if you strip it to the very basics, it is basically a random variable. It's a random vector in a very high dimensional space. So if you look at an image, it's a very high dimensional vector, maybe 1 million, 3 million, 5 million dimensional vector. And that vector sits in a very high dimensional 3 million dimensional space. And so you can plot all the images that you can understand, you can see, and imagine that these are all points in a 5 million dimensional space. Okay. Now, some distributions are important. So if you think about this particular scatter plot in 3 dimensions, we see that there is a bowl kind of shape, and all the points are along that bowl shape. So basically, there is a manifold, and all the important data points actually lies on that particular manifold. So let's not worry about the projection part. Let's just look at the actual 3D figure of the scatter plot. And basically there is a nice shape. And what that means is even if you look at this 5 million dimensional space and you plot all the images in this 5 million dimensional space, what you will notice is that the distribution is actually on a very low dimensional manifold in that high dimensional space. So by manifold, what I mean is it has a surface, like it looks like a surface in this high dimensional space. So it's not like a solid ball. It's not a solid ball that you're seeing. What you're seeing is basically a surface in this high dimensional space. So what do we need to do in order? So this is the content that is useful. So all the useful content that you can think of is basically lying on this manifold. And what you want is, given the prompt, what is the point from this high dimensional space that you want to pick as a result? So we want a function that takes as input a prompt, which is a high dimensional vector, and then creates content, which is again another high dimensional vector, but it lies on a manifold. So in good old days, a trained person would execute the function. So I will say I need a picture of a duck, and then somebody like a painter would then draw the picture of a duck. Because the person has this function f in their head. But now because we have a lot of prompt and content pairs, so we know duck and a duck picture, and then we know cat and a cat picture, and we know dog and a dog picture. And we don't have just one picture. We have like millions of pictures of dog, millions of pictures of cat, and so on. So we have a lot of prompt and content pairs. And then the only problem is now we need to learn this function f so that we can execute the function on a computer. So here is the idea. We want to derive a function f that maps prompt to content. I'm going to make things a bit more formal. So z is the space of prompt, x is the space of content. Mu is the distribution over z. So mu is the probability distribution over the space of prompt, and nu is the probability distribution over the space of content. P is the joint distribution over the prompt content pair with marginals mu and nu. So P is basically it's a joint probability measure over the prompt content. So duck, it's the measure between duck and the duck picture, and cat and a cat picture, and dog and a dog picture. Right. So that's the prompt content pair. And then we want the function f that maps z with measure mu to x with measure nu. And we need a good function approximating classes to derive f from the data, whatever data prompt content pair we have. So there are two essential problems in generative AI. The first one is we just want to generate a content where the prompt does not matter, but it can be used as an intermediate step. So I want a picture of a human being. So we have, let's say that's what I want, a random face of a human being. I don't really care what the prompt is. All I care about is I need a picture that kind of resembles like a human face. Okay, so that was the original problem of generative AI, and a lot of people worked on it between 2008-9 to 2017-18. And then the second problem is I give it a prompt which is generated according to the measure mu, and we need to generate a content X based on the prompt, but it needs to have this conditional distribution P of X given Z. So in this particular case, the prompt matters. The generated content must be a function of the prompt, and the generated content must meet the distributional requirement. And the examples of this is the large language model and diffusion model. Essentially, in this case, if I ask it to create the picture of Barack Obama, for instance, so then it has to give me a picture of Obama. It can't just give me a random human face as an output. So you might wonder what's the difference between the traditional machine learning algorithms and this new paradigm, because even in traditional machine learning algorithm, we have like the training data, and we push the training data through a training process, and then we get a function that kind of mimics the classification or the regression performance. And it's kind of sort of like that, but there is a subtle difference here. So in supervised learning, you have the training data and you get a function f, but typically x here is a low dimensional vector. It could be 10 dimensional, 15, 20, 100, 200 dimensional vector. Okay, in generative AI, you have the prompt and content pair, and the goal is to train a function that has a very specific distributional output. which means that f of z must be distributed according to px given z. So and also in Gen AI, X is typically very high dimensional. So the output here that we are looking for is extremely high dimensional. It could be an image, song, or a paragraph of text. So the dimensionality of the content and the requirement on the terminal distribution actually changes the whole game from what it was in the case of supervised learning, which is something we are all familiar with. So you might wonder, okay, so now that I understand what essentially we are trying to do, we are trying to find a function f that maps z with measure mu to x with measure nu. What kind of functions can we pick? So we can pick linear functions. Of course, this is going back to 1940s and 30s, when it was the easiest. Linear regression was like one of the first regression algorithm. Then you can use one layer neural network. Then you can use reproducing kernel Hilbert space. You can use recurrent neural networks. So all of these things are tried. So one layer neural network, 1950s, reproducing kernel Hilbert space, maybe 1940s, 50s, 70s. Recurrent neural network, 1990s. Deep neural network, 2010. Convolutional neural network, somewhere around 2011, 12. Okay, so all of these functions have been tried already, and then transformers, which is 2014, 15 onward. Of course, people tend to say that transformers is something that was designed in 2017, but actually there's a lot of history to it, which is actually there in the 2017 paper that people tend to refer to. So the idea of transformers was already there in 2013, 2014. It's just that people didn't know what is the right architecture for it to work. And so the right architecture for transformers actually came in 2017, which led to all the benefits of development of Gen AI systems. Now you can imagine linear regression is something we can run in like seconds. Transformer training is something that happens over months, and then there is everything in between. So large models are definitely difficult to train because of the humongous data set it needs to train the model. So what do we know when before we start the training of a generative AI system? So we have many samples of the content where the content is distributed according to a measure nu, and nu is unknown. So remember when I was mentioning about this images lying in 5 million dimensional space, we don't actually know what the distribution looks like because we can't really imagine what things look like in a 5 million dimensional space. We know the math part of it, but we cannot visualize it, right? So we don't know what this distribution nu looks like. Is it Gaussian? Is it non-Gaussian? Is what kind of mean and covariance matrix it has, if at all it is Gaussian. So all of this thing is unknown. Of course, if it was Gaussian, then it would be easy to estimate the mean and covariance matrix, but the fact is it's not Gaussian. It's some other complicated distribution. So in this case, if we are not given any prompt, so we have like a bunch of human faces, and then we want to train a generative AI system where I press a button and it generates a human face of the same distribution. Then in that case, I don't have any prompt associated with it. And then you can estimate nu and you can draw a sample from nu using Monte Carlo methods or sequential Monte Carlo methods. So these are the topics that I think people studied in 1980s to 2005-ish. People were studying sequential Monte Carlo methods for generating XI. But remember in sequence, so why were people studying sequential Monte Carlo? So they wanted to, the origin of sequential Monte Carlo is they wanted to figure out when is a particle, like we have this boson, photons, all these particles that physicists think about. So they wanted to know when are these particles going to collide with each other, when are they going to disappear, when are they going to appear. So all of that simulation requires Monte Carlo simulations, and so physicists came up with this idea of sequential Monte Carlo simulation, which can be used for generating a sample as well, because that's what they were doing. Except that sample that they were generating is when is the particle going to die or when is the particle going to succeed. So they were actually looking at just one-dimensional objects. So Xi was just one-dimensional. It's probably just time or something like that. So very small dimensional objects. Then the second case is when I don't have any prompt. So in those cases, we can generally assume that mu is a Gaussian distribution. So the prompt prompt distribution is a Gaussian distribution, and Zi is an independent sample from this distribution, and Fz is distributed according to nu, which is the distribution of the content. And the last case is when Zi is specified for each xi. So I say that this is the image of Obama, this is the image of Michelle, this is the image of Trump, and so on and so forth. So now we have a prompt associated, we have a name associated with the image. So then we have a prompt content pair. So Zi is specified for each xi, so prompt is specified for each content. And then there is a map G that maps the content to the prompt. So I have a mapping which classifies the image into this is the image of Obama versus this is the image of Trump, and so on. Sometimes these mappings are unknown and it also needs to be estimated. So what's the general recipe for coming up with generative AI models? So typically you pick a function approximating class. It could be neural network, it could be convolution neural network, it could be transformer. You are parameterizing it by theta. Theta is a subset of Rn. But here, remember that in the case of LLM, this n is actually trillion, like of the size of a trillion. It's of the value in the order of trillions and billions. So it's not necessarily just a small like 5-dimensional or 10-dimensional vector that we're talking about. A loss function that measures the performance of the function f theta that maps prompt to content. And then we want to solve this minimization of this loss of the function f theta using stochastic gradient descent or some other method, which we are not going to cover in this particular presentation. Okay, any questions so far on this part? No? Okay. So here is the key idea. So I'm going to look into the case where prompt dimension is much, much lower than the content dimension. So prompt dimension could be a 1,000,000 dimensional object and content dimension could be a 1,000,000,000 dimensional object. So those are the, like there is an order of magnitude difference between what the dimension of the prompt is and what the dimension of the content is. So there are two ideas here. The first idea is where I generate from prompt, I generate a content using some function f. And then I discriminate whether the content is correct content or a random content, I like a not true content. So I give it a prompt, give me a human face, and it generates some image. And then the discriminator says whether it looks like a human face or it doesn't look like a human face, something like that. And then the second idea is where the x is first compressed to a small dimensional vector z. And then then there is another function f that maps z back to x itself. So this is known as an autoencoder model, where you are first compressing x and then you are trying to recover x from the compressed version of x. So these are the two ideas. And so the first idea is basically the basis of generative adversarial network, where you have two deep neural networks or convolutional neural networks. One that takes a random vector z, could be a Gaussian vector. It could take a Gaussian vector and then it generates an image, and then the discriminator basically deduces what's the probability that x is real in this case. And if x is real is true, then it means that this f theta is a very good generator of images or of whatever content you need. Right. So this was, I think 2014 is when this particular method was invented. And basically the idea there is that you want to minimize over all f theta and you want to minimize over all discriminators of some objective function. So this is the loss function L of f theta that I was alluding to. And you can solve it using alternating minimization and maximization operations to get the optimal f theta star, which is the generative model. So generative adversarial network was very famous at some point of time. Because it was generating a lot of realistic images and there was a lot of excitement around GANs, but it was also extremely hard to train. So you had to do a lot of fiddling around with hyperparameters, and there were like 1,000 variants of generative adversarial network in order to make it robust to all kinds of tuning, hyperparameter tuning. But to a large extent, people were unsuccessful in creating a very robust generative adversarial network, which could work for a large number of situations. So I would say that even though there is quite a bit of research in generative adversarial network, I think that the general consensus is there is no production system, industrial production system, which is using the GANs at this point of time. The second set of algorithm is autoencoders. Here, remember there was a compression function that was compressing the content to a smaller dimensional z, and then from z you wanted to recover x. So here the loss function is basically the recovery loss. So this is the distance between x and whatever is coming out of f theta g phi of x, which is minimized over both f theta and g phi. So you want to optimize for both g as well as f. The problem here really is that the distribution of z, so you want a generative model, so you want to give it an input and you want to get an output. Now you want cat images, so you've gone through this whole autoencoder thing. The problem is that whatever distribution z has for all the cat images that gets inputted here, it's not very clear what kind of distribution z satisfies. So now if you want to generate another cat image, you don't know how to pick a good value of z in order to generate a random cat image. So again, this was problematic. So therefore, they came up with what is known as variational autoencoder, where now z is required to be a Gaussian distributed random variable or random vector. So this x is a million dimensional, z here is maybe 5,000 dimensional or 1,000 dimensional. And then you want to recover x from this 1,000 dimensional vector, and you want this 1,000 dimensions to have a standard Gaussian distribution. So you pick mu to be a Gaussian distribution. So mu is the distribution of z. And then you want to minimize the KL divergence between the distribution that is coming out of z, g, and then the mu, which is the distribution mu you want for z, and then some other function of this particular training loss. So this is basically the loss function that we need for training variational autoencoder. So that's the method for solving. So variational autoencoder is again something that was, as you can see, this is a 2013 paper, and then a lot of work was done between 2013 to 2016 to develop this theory of variational autoencoder and improve the implementation. And to some extent, it's actually a very good generative model, but not for very high fidelity images and for very high fidelity, but very high dimensional video and audio and so on. But it can do like handwriting, like if you want to generate numbers 1, 2, 3, 4, handwritten numbers 1, 2, 3, 4, you can do that for variational autoencoder because that doesn't require, it doesn't have very high dimensional objects. Now let's look at the case where prompt dimension is equal to content dimension. So content is a 5 million dimensional vector. It's an image. So image could be 5 million dimensional vector. And then we want the prompt dimension to also be of the order of, not be of the order of, it has to be exactly equal to 5 million dimension in this case. So the idea here is that I want to compute an invertible dynamic. So basically I start with x, I start with the content, and I create an invertible function f, and I generate the content, the prompt z out of it. And then I want to invert I want to use the inverse of this particular function here. So from z, I can then recover what x is going to be. And the key idea here is that if you look at the density function across this particular transformation, you can actually compute the density exactly by knowing what the density over x is. I think this should be z here. This is x here, but it should actually be z. So d mu by dz evaluated at f inverse x, right? So once you know, so because you know, so all you need to know is what is this invertible function f inverse that you need to pick. So this is what you want to train. And the key idea here is because you can figure out what the distributional dependence between the two dimensions is. And that's what they are trying to exploit. So the first idea is normalizing flow model, where you pick like a neural network, a sequence of neural networks, each with a determinant not equal to 0. So determinant of x of f theta k. So f theta k is the kth layer of the neural network. you take the derivative with respect to x and you want this determinant to be non-zero. And you can do this by by putting some constraints on the weights of that particular layer. So it's not something that is impossible to do. And here the loss function is some divergence or metric over these two measures. So one is the push forward measure of mu and the other one is the measure nu. So you want this particular measure and the push forward of mu to be equal to each other, and that's what this particular algorithm is trying to do. And the last one is diffusion model. So diffusion model is what has become very common right now. Here the idea is that you start with the image and then you progressively add noise to the image. So that is equivalent to running this called an OU process. So you start with an image, you keep adding noise to the image, and then you try to filter the noise in the backward. So the cool thing about this particular process is that it converges to Gaussian distribution very, very fast, exponentially fast. And then this particular process is invertible. So that's the other benefit of this particular process, this stochastic differential equation. So what you do is you start with an image, you keep adding noise to the image, you get like a Gaussian distributed image at the end. And then what you do is you run this backward. Remember, it's an invertible function. So now you run the backward process. And then what you get is you start with, so the backward process, you start with a random noise and you get a actual image, which is distributed according to nu. So this is the way to transport the measure. And so how you implement it in reality is you discretize this particular stochastic differential equation, and that gives you the diffusion model. And so the company called Stable Diffusion, actually, they are essentially using a variant of this particular method in order to generate images, realistic images. And again, remember that we all know what doesn't work. So we know the variational autoencoders doesn't work. We know that the autoencoders and other thing we discussed doesn't work. The generative adversarial network doesn't work for images. It just turns out that this diffusion model works wonderful for images. Okay, so now a lot of realistic images are coming out of diffusion model, which is basically the mathematical underpinning is right here. And now there are a lot of new methods that are coming up. So these are all. So diffusion model was introduced to the computer vision literature in 2015. In 2014, 2015 is when this particular method was introduced. So at this point of time, the methods that are getting introduced is diffusion Schrodinger bridge method, and then some other methods based on optimal transport theory. So a lot of these methods are, again, over time they will be tested, and some of them will be good for something, some of them will be bad for something. We don't quite know how this particular field is going to evolve in the future. But know that there are many other models that people are trying out at this point of time. A lot of it is in applied mathematics / theoretical literature, and not necessarily in the practical world at this point of time. And of course, all of this training costs millions and billions of dollars. So somebody has to be comfortable enough to put in $1 billion on this, whatever this diffusion Schrodinger bridge method is, and then hopefully something will come out of it or nothing will come out of it. So we don't know. So it's a bit complicated whether other methods will emerge or not, because now we know that one winning solution works, then nobody wants to touch anything else because it's so costly to train another method. So this is something in both these algorithms, we had an invertible dynamics, and then we inverted the dynamics in order to get the generative model. And then computational optimal transport is another emerging method in this area. Now we'll talk about the case where prompt dimension is much, much higher than the content dimension. So this is basically the case in large language models. So we have the prompt, which is the past 24,000 words, and the content is the next paragraph. But the way many of these LLMs generate paragraphs is not by generating a paragraph, but they generate words, one word at a time. Okay, so the way, because paragraph is a sequence of words, we get like the probability of next paragraph is probability of word one past 24,000 word multiplied by probability of word two past 23,999 words, and the first word that was generated here, and so on and so forth. Okay, this is not an exact equality, by the way, this is an approximation. So don't think of it as exact equality, but this is how basically you can think of how paragraphs are generated, or how even, my words are getting generated in my mouth. Like my brain is doing all this 24,000 words and 23,999 words. All of this is happening in my brain. And that's how I'm generating new words and new paragraphs and so on and so forth. So all we need to do is, what is the probability of the word given the past 24,000 words? So as long as I can come up with a very good probability measure for this, then I can generate as many paragraphs as I wanted to, and the rest will be taken care of. So here f theta is basically the space of transformers with self-attention mechanism. So that's the specific function approximating class. And what we are doing is, we have like the probability, this f theta based on all this prompt is basically a, I don't know, 50,000 dimensional vector, which is the probability of first word in the dictionary, second word in the dictionary, third word in the dictionary, and so on, based on the past 24,000 words. And then you pick the one with the highest probability or the best match, pick that particular word, and then you send it out as an output to the user. Why self-attention transformer? So people have been, like the theoretical people have been looking into it for quite some time to understand what exactly is transformer trying to approximate, what kind of function does it approximate. So there are some work, unpublished work at this point of time, which is basically establishing that either self-attention transformers are universal function approximators, either for some definition of permutation equivalent functions of matrices, or predictor of order L ergodic Markov chain. So this is something that's still an ongoing area of research, but it will take some time to understand what exactly is transformer good for. We don't quite know yet. We do know that neural networks are good for any continuous and bounded function. So there is a lot of literature on that, and then neural networks with a certain weights, like if the weights are non-negative and stuff, it's a universal function approximator for monotone functions. So a lot of these things are something that is well known, but we don't quite know what self-attention transformers are good for. So it will take maybe 10 or 15 years to know what exactly self-attention transformers are good for. So in the future, we are going to see a lot of mix and match generative AI models. So the things that people are looking at right now is, how do we reduce the size of the generative AI models? And like I mentioned, there are a trillion weight vectors. So the theta that I was talking about, it could be a trillion dimensional object. So how do you compress a trillion dimensional object? And the idea there is, we can just quantize them. Okay, so if it is 0.11111, I'm just going to make it 0.1 in the memory, and then hopefully, if I quantize everything in like 4 bits, so instead of having 64-bit or 128-bit values of every value of theta, like every element of theta, I'm just going to have 8-bit reserved for every value of theta, and I can just compress the entire function very quickly. So there's some of that going on. Some people are trying to figure out different ways of training algorithms so that we could optimize the training time of some of these models. The key idea there is, instead of generating an image which is 5 million dimensional big, what we will do is we will convert the prompt to an image which is only, I don't know, 500,000, like 100,000 dimensional big. And then we are going to upsample that image. So we have like a small image, and then we will upsample it to create a very big image. So a lot of those algorithms are also getting used in order to improve the performance and create cheaper generative AI models. There's a lot of innovation happening in this particular area. And then the other idea that I have, which I'm not sure how many people are using, but a lot of these training algorithms uses scale divergence. I'm not a huge fan of KL divergence, but if it works, it works. I'm no one to blame or no one to raise an objection. But I really feel that we should try out other divergences as well to see if the training is effective, the training is fast, if it requires fewer samples, or if it is simpler computation. I just don't know why everybody is using KL divergence. But it seems to work, so I can't conclude. So to conclude, generative AI is basically mapping input to output. We've all done input to output mapping all throughout our life, but there are some peculiarities here. One of which is there is a very strong distributional requirement of the output that is coming out. The output has to look like a real image. It cannot look like some random gibberish. And the output has to look like a real text, a real coherent paragraph. It can't be some random words coming out of a system. So that's one requirement. And the other requirement is these outputs are extremely high dimensional, 1,000,000 dimensional, 1,000,000,000 dimensional, and so on. So that's where generative AI is basically very, very important. The theory has been, of course, known for decades. I said that there are connections to particle physics, there are connections to optimal transport theory, connections to optimization, and so on. A lot of connections, a lot of things that we have already known for several decades. And so all of this is coming together to create a technology that is useful for a wide range of businesses. So that's all I have. I'll be happy to take any questions. And hopefully this will sparkle some debate about where you can use it within your own research.
Questions from the audience here or from the people online? Please use the Q&A. The chat has been disabled. You want to ask questions?
Yes.
I think right at the beginning, you were talking about data has like a manifold.
Yes.
Is that just because of the things we put, like, language has grammatical rules?
Right.
And so it's not some semantic free,
Okay.
like, bunch of random
That's
words.
right.
And
That's
then,
what is creating the manifold.
and then like images, like all animals, they have eyes.
Okay. Exactly.
And, okay, so it's, in theory, it could be a ball, but just what we're putting into it biases.
That's
the
right.
shape.
That's right. Exactly. So a random image is just black and white dots, pixels, right? But because human face has two eyes, a nose, lips, whatever, there's color pattern, the way the light shines on our face, there's like a pattern of color that emerges out of it. So all of that actually leads to a manifold in this particular image light. Now those manifolds need not be connected. You can have like a bunch of a manifold here and a manifold here, and that could is disconnected. So for instance, the cat manifold is here and a dog manifold is here and a human manifold is here. So it could be disconnected. It doesn't need to be connected, but these are just a bunch of manifolds in that high dimensional space.
Okay.
And so one of the ways by which people are, so another faculty here, Alish, who's now at Amazon, he was working on how do you transform the face from one face to another. And so what he was doing is he was sliding along the manifold and the face would turn from a child face to an old person's face or a man face to a woman face and so on and so forth. So all of that is something that people have tried. Just by sliding along these manifolds.
Would you-
all to do it.
Give it a prompt and then it moves? Or-
No. They just move remember all the prompt gets converted to high dimensional vector. So they just move the vector.
Okay,
And then they pass it through the function f and then you look at the output image and it just changes. Yes.
Is there like any algorithm to identify something that's been generated from generative AI, or like something to go backwards and say, okay, this was generated? I don't know.
Unfortunately, no, because
Because you were talking about inverse functions and these things, so I thought, can we invert this process? Like
you can invert it and you can get the dimension like a prompt
That's-
like this, that vector z, but whether that
It doesn't
vector
tell
z is a human generated vector or maybe that's one way to test, but it's quite unlikely that the human generated vector z and the machine generated vector Z would be different. I don't know. It's a good thing to try, but I don't know if it's possible. Oh, I think there is. What kind of Gen AI you think will work for dynamical systems? Do you have any suggestions? Not really, because the thing is we tried, so we are a theory group, so whenever we come up with an algorithm, we need to prove that the algorithm works for the specific system that we are trying to develop. So we tried some generative AI development for Markov chains, but we couldn't prove it. And now we know why we could not prove it. Like we spent like 6 months trying to prove that it will work for all Markov chains, but it did not work out. The proof did not work out. But in simulation, it was doing reasonably okay. Now we know how to fix the proof, but we haven't gotten back to the problem yet because the funding was, we didn't have funding to work on that project anymore. So anyway, we don't know what will work. We've tried it, but we don't have any success stories to report. So the question was, how do we use Gen AI techniques in science and engineering beyond text generation? So I think we covered a little bit on that here on this particular slide number 5. So we can use beyond text generation, we can use it for user generation, which is basically for app testing and so on. So we can use it for user generation, for app testing, we can use it for vulnerability detection in software systems, we can use it for marketing campaign generation or travel itinerary generation. It is already being used for medical image cleaning. So a lot of places where generative AI could be used, but I don't know why, maybe people are not working on these other topics. I really don't know why people are not looking into it. Or maybe somebody is looking into it, it's just that we don't know about it. That could also be the case. Can we use these methods to predict continuous time series data from discrete data as input? So it is definitely, so theoretically it is possible, but what generative AI model you want to use in order to do that is not very clear, because at that generality, we don't have any off-the-shelf algorithm to try and test. If I recall correctly, I know some researchers who are trying to do weather prediction using generative AI models, so they give it as input the weather for the last 24 hours and they want to figure out what's going to happen over the next 3 hours. So that kind of stuff is also something that people are trying, but again, these are very large scale problem statements, so it requires a lot more funding to be able to come up with what is the winning solution on this particular problem. How many data points are necessary for training Gen AI generally? It depends on the function size. So going back to this particular slide. So remember, we have 3 things here. One is the input vector, the prompt vector. One is the output vector, which is X. And then what kind of function approximating class you're picking, which hopefully contains the function you're looking for. So if you have 10 dimension here, 10 dimension here, and you're using just linear function, then 100 data points are good enough. If this is a million dimensional and this is a billion dimensional, and you're using transformers, then you need like terabytes of data to be able to do this training. So there's no general rule actually, but I think the way to think about it is you can maybe multiply the dimension of Z with dimension of X with the complexity of the function that you are picking, and you will get a rough idea of how many training samples you're, but this is just something that I'm making up right now, but it just gives you an idea that it all depends on the dimensionality of these spaces as well as the complexity of the function approximating class.
Raj, do you have a question?
Yeah, I had a question.
Yes.
So Professor, a couple of days ago, I found a paper from Transactions on Intelligent Transportation Systems, IEEE, and that paper was about using ChatGPT as a co-pilot. And then I thought I'm never graduating. But then I read the paper and then what these people did, like they asked ChatGPT, okay, I've given you a selection of controllers
Mhm.
in only MPC,
Right,
a Stanley and one other controller.
right,
And now you have to plan a trajectory from
Right.
this point to this point, and these are the obstacles.
correct,
Tell me what's the best controller.
right,
And it somehow did something
right,
and told something. But then the paper claimed that, yes, so using this chat GPT, we can guarantee safety that yes. So I'm like, is that possible? Like, I read Kolmogorov's book and it doesn't seem to be possible.
No, it's not possible because safety necessarily means that the output satisfies certain constraints throughout the trajectory. And ChatGPT doesn't prove any theorem in the sense that whatever the output ChatGPT is going to give, whether it's correct, wrong, satisfies constraint, doesn't satisfy constraint, is something that you cannot readily verify. So I wouldn't trust too much. Like I know like a lot of people are getting like trading ideas from ChatGPT. Do your own research. I don't think it will work. But hopefully I'm wrong. Maybe 10 years later I'll be proved wrong. But at this point of time, I don't believe that it is giving an output which is provably safe. Okay, so any other question inside the room before I jump onto this question? No? So the question is, you discussed how diffusion models are built on a dynamical framework, but everything else you covered has a feed-forward flavor. Given that our brains do their computation in time via dynamics, why are our artificial systems so feed-forward? What discouraging research on better RNN? You know, I don't quite know the answer to this question. I think the problem with there are two issues here. One is how our brain functions. So there is like a competing theory about how our brain functions, and maybe our brain is not functioning by adding weights, but by frequency of pulses, electrical pulses, that are being sent from one neuron to another. And so for that, there is like the neural network doesn't really accurately depicts what's happening in the brain. So there is one of that theory, and I don't quite know biologically what's happening in our brain, because of which we have our intelligence. But as far as discouraging research on RNNs is concerned, I think the critical factor there is stability of training, which is we don't quite know how to train RNN in a way that provides reliable output in production systems. So in experimental system, yes, you can get it to work, but whether it will work under all circumstances, under all different prompts, and so on, people don't generally know. And there is like a whole bunch of papers written on why training RNN is difficult, and nobody has been able to follow up on that and come up with a better algorithm for training RNN. And then it's not even clear if you come up with a robust way of training RNN, it's not clear whether it's going to give you desirable results. So that's probably what is discouraging research. So, as much as we would like to think that, okay, research happens because people want to find the underlying truth, the fact is research happens because something is more in vogue than others. And so right now LLMs are vogue, so everybody is working on LLMs, and so somebody is driving an autonomous vehicle using LLM. But that does not mean that things should happen that way. What strategies are there for reducing high dimensional outputs into low dimensional inputs accurately? So the strategy is basically just feed a neural. So you give 1 million dimensional input to a neural network and you force it to have only 1,000 dimensional output. And that's how they are trying to embed a 1 million dimensional vector into a 1,000 dimensional object. So that's how you are getting the low dimensional inputs from. Are there any ways to constrain GenAI with physical laws like conservation of mass or energy to avoid hallucination? This is a great question. Actually, so if you look at the text, there are no conservation laws of text. There is, of course, grammatical rule that I'm pretty sure they have like companies like OpenAI would have some ways of making sure that the grammatical rules are followed in the output. But as far as trying to accurately model a dynamical system, I think something like that would be very useful. But again, those things are not something people are working on, so we don't quite know if somebody comes up with a dynamical system model generation, like a digital twin generation using generative AI, I guess they will have to use conservation of mass or energy to come up with better results. So one thing I can give you is, when I talked about people are trying to come up with climate models using LLM, they are using the PDEs that influences the movement of air and moisture and all that stuff in the air. So they're using those PDEs explicitly in the training process so that LLMs generate output that satisfies the physics, the PDEs that comes from physics of how the climate behaves. So people are using it in other areas, just not necessarily in areas that you might be interested in.
Thanks, our speaker once again. The other one, go over time too much, I know there are so many questions, we're like, we're trying to get ideas for PhDs. So, yes. thank
I
you.
think we covered all the.
Yes. Fortunately, I didn't see my Q&A was empty, so
Yours?
my Q&A was empty,
Okay,
so we didn't see any of these questions.
I feel.
All right,
Okay, thank you so much.
thank you so much. Sorry.
Could I enter the recording?
Yes.